Hello, this is Jim Corkins, and we are continuing on with Module 5 on rotation, and specifically we're moving on to section 5.3, and I'm assuming that you've already kind of gone through torque, and you kind of understand the basics of torque, of the introduction of torque, which was in 5.3.0. So now we're moving on to what is called statics, and statics is a part of torque. And it's the beginning where we're talking about where a lever arm is in a static condition, meaning it is not accelerating or speeding up as it's rotating clockwise or counterclockwise. So if you haven't done the reading, please take the opportunity and do that sometime soon, before or after doing this video. In OpenStax, it'll be in Chapter 6, whether you're in Physics 111 or 121. And if you're using the Coletta textbook, it'll be Chapters 9 and 10. All right? So, some assumptions that we could make about static equilibrium, that's kind of saying something is in equilibrium in a force diagram, meaning it's moving at a constant velocity, or it's not moving at all. Well, with torques, it's saying it's not rotating, meaning alpha is going to be 0. Or it could not be rotating at all, or rotating at a constant rate. So it could be not spinning, so omega is equal to 0, or it's spinning at a constant rate. Either way, alpha is going to be equal to 0. So that's one of the assumptions that we're talking about with static equilibrium. Another assumption is that you could choose any point to be your pivot point. Since there's no net torque about any point, no matter which point you choose as your pivot point, that sum of those torques will then be equal to 0. So since the sum of torques is equal to 0, you could choose any point along that lever arm or to be your pivot point. So one strategy that we're going to see is we want to probably choose a point that will optimize our problem. And we'll get into that when we're talking about, there's a bicep problem that we're going to do a little bit later with an arm. Okay. All right. So there's some strategies to doing these problems. Again, you could pick any point you wish as a pivot point. One of the things we're going to do is we're going to determine all forces about a pivot point. So we're going to sum the torques, but we're also going to sum the forces about a pivot point. We're going to sum the forces in the x direction, sum the forces in the y direction, and we're going to sum the torques. Okay. And we're going to want to do all three of those simultaneously because we could then use some of the equations from the x direction forces and some of the equations in the y direction forces along with the torques to kind of help us solve more complicated problems. Okay. So the first introduction to statics is this is a great problem. It asks you, so suppose you have a lever arm that's connected to a point right here. So this is the pivot point, the black dot. And this lever arm is a distance 1 meter long. And at the end of this lever arm is 1,000 Newton weight attached right here, pulling down. Here's a scale that's pushing up at the lever arm at the halfway point, so at the half-meter mark. And the question basically is asking, what would the reading on the scale read? If the scale is here and the lever arm and the weight is out here, where the pivot point is at this point. So take a moment to try to think about the problem. Here are your choices: 500 newtons, 1,000 newtons, 2,000 newtons, or 4,000 newtons. What would this scale read? So pause the video now. Okay, so you're probably back. Let's go ahead and try solving this problem. We're going to try to solve this problem using this strategy right here. So what I like to do is kind of mark up and do my force diagram on this actual, just to give some context to the problem. So what I'm going to do is I'm going to mark this up. and do it this way. All right. So here's what I'm going to say is right here. This, again, this is a weight. It's going to be pulling down on this lever arm. And this is 1,000 newtons pulling down on this lever arm. Okay? Over here, I'm going to keep this black, and we'll keep this as purple. So right here you have a scale. It's going to be pushing up on the lever arm right here. And that force right here is, we're going to subscript this as the force of the scale. Okay? So what we could assume too from this is that there is another force at this pivot point. So if the scale is right here and you have a weight pulling down, interesting thing is there is probably, this lever arm is probably being lifted, right? If there was nothing holding this in place right here, this lever arm in place, this part would just flip up and flop over, right? So what I'm guessing, and I'm pretty accurate in the way I'm guessing, is that there's another force here right at this pivot point that is holding this lever arm in place so that it doesn't flip and fall off. So I'm going to just call this force at the pivot point, and that's kind of an unknown force to the problem. Okay? And I don't know about its magnitude in relationship to these other guys here. It's probably the same size as this 1,000 Newton force. I don't know. But what I'm figuring out is that this force at this pivot point is kind of like, if this is a teeter-totter, this is going down, this side would go up, and so that means there's another force here holding it in place. Okay. Anyways, by this basic analysis, that there's a force at this pivot point, let's go ahead and do a real quick force diagram. So again, I want you to always practice doing things correctly, and I always want you to make a coordinate system with your force diagram. So the x direction, this is positive x direction, this is a negative x direction, this is a positive y direction, this is the negative y direction. Okay, so we're going to attach some of these forces here. Okay, so the first force I'm going to attach is the force due to this pivot point here. So that's the force at the pivot point. It's pointed down, and I'm going to label this negative F sub P. Since the force is pointing down, that's why I gave it the negative, and that's negative F sub P. Nope, I forgot to put my little vector heads on everything here. And there we go. Moving away out from this pivot point, now we get to the scale. I have a force up due to the scale. And moving further out, I have another force down. Again, I don't know the sizes of these, but I'm going to assume. I'm just drawing down arrows. I don't know about if they're proportionally even, but it seems by logic they would be. Okay. So here's our basic force diagram. Okay. So we have 1,000 newtons down to match this. We have the force at the pivot point down, and we have the scale up. So we're going to sum our forces in the y direction. Okay. I'm going to do the scale force first. Then I'm going to do the pivot point force next. Force at the pivot point. And then I'm going to do the 1,000 Newton force. Do the weight here. I'm going to set this equal to mass times acceleration. But since, again, since it's in a static state where the velocity is 0 and the acceleration is equal to 0, we could say that this is all going to be equal to 0. Okay? My guess is if this is a pivot point right here, that this is kind of like a teeter-totter, that this force down is balancing out with this other force pulling down over here. And this is holding the entire system up. So my guess is this is, I'm going to make some probability guesses here, that if I bring these two forces onto the other side of the equal sign, that I'm going to get the force of the pivot point plus the force of the 1,000 Newton weight. And if we assume that that pivot point right here, force of that pivot point is equal to 1,000 newtons, that this is probably 1,000 newtons as well, and that this force due to the scale is probably going to then read 1,000 newtons plus 1,000 newtons, which is going to be 2,000 newtons, right? It's probably going to read 2,000 newtons based on just common sense stuff. But what I think we should do is we should sum the torques, okay? So there's a couple things that we had noted from our static equilibrium problem. It said sum the forces in the x and y direction. But what we want to do is we want to determine the sign of each torque about the pivot point, and I want to also determine the distances. I want to draw the distances and also the angles too. So I want to have all the information right on our drawings, okay? And we're going to want to take a pivot point which takes some of the unknowns out of our problem and makes our problem easier to solve. So what we're going to do is we're going to, we need to choose a pivot point. Well, we're solving for f sub s. We need to keep that in the problem. And we also want to use, this is the only number that we have, which is 1,000 newtons. We need to keep that in the problem. So since we could choose the pivot point, which is by the problem right here, we could choose the scale or this. We could choose any one of these as the pivot point. But since we don't know for sure what that force is on the pivot point, I think we want to choose this as our actual pivot point. So I'm going to put an X there. And that means since torque is equal to RF sine of theta, since this R is the distance from where the force is to the pivot point, since this force is attached at the pivot point, R is going to be equal to 0. That means this force is not going to be in our problem at all. So we're eliminating that unknown. Okay. So here's what I want to do. So given that that's the pivot point, we don't have to worry about this force. But starting from the pivot point going out, I want to determine the basic, I want to find R and theta and the direction that this force is going to turn this. So if this is a lever arm, this force is perpendicular to that lever arm. So the sine of 90 degrees is going to be equal to 1. What I also want to determine is if this force is going to spin our lever arm clockwise or counterclockwise. So if this is our pivot point and this is the only force here, it would be pushing up on the lever arm and spinning it in the direction that my cursor is turning. And so that's going to be a positive, that's counterclockwise, so that's a positive Z torque. So this is a positive Z torque. Okay, that's not always to say that an upward, a Y direction force is going to always be a positive Z torque. If the force was over here, let's say the lever arm was over here, an upward force would turn it clockwise. Would be turning it clockwise, which would be a negative Z torque. But because this force is on the right-hand side of the pivot point and is pointed up, the positive Z just happens match up with the positive Y by accident. Okay. Also, we want to note that the location of the force. The force is located at the halfway mark too. All right, let's mark up this force. This force is also 90 degrees. This negative Z4, this 1,000 Newton force is directed downwards, which would be spinning this lever arm clockwise. Okay, so that's going to result in a negative Z force, a negative Z torque, and this force is located 1 meter out from the pivot point. So let's sum our torques here. So we're going to sum our torques and see what we get. So starting from this point out, again, we don't need to worry about this force. We get to our purple force. So that purple force is going to be a positive torque. It's a positive Z torque. It's 1/2 meter out. That force is F sub S. And it's the sine of 90 degrees, which again is just equal to 1. So that means this is going to be positive 1/2 meter times F sub S. So that's what this torque is going to be. Again, moving further out, starting from the pivot point, moving out, we get to this force down. So this is going to be, it's going to be a negative Z torque. It's 1 meter out. It's 1,000 Newton force. And this is located, this is at the sine of 90 degrees. So again, that's equal to 1. Okay. Going to move this over so I have enough room. Well, summing the forces, you set that equal to mass times acceleration. Summing the torques, you set that equal to I alpha. But since alpha is equal to 0 here because it's not moving or accelerating in any direction, then this whole thing sums to 0. Okay. So this torque right here is just 1/2, it's a 1/2 meter, F sub S. This is 1 meter, 1,000 newtons. Again, this is just 1. And this is going to be equal to 0. All right, we're going to bring the, so this is going to work out to be, I'm going to actually write this as 0.5 meters. F sub S, and this is going to be 1,000 Newton meters, and this is going to be equal to 0. I'm going to add this 1,000 Newton meters onto the other side, which means when I bring that onto the other side of the equal sign, what we're going to have is 0.5 meters on this side times F sub S, and that's going to be equal to 1,000 Newton meters. Moving this down, now what we have to do is divide both sides by 1/2. Okay. So when we do that, we're going to have F sub S on this side. And then on the other side, we're going to have 1,000 Newton meters divided by 0.5 meters. And what this works out to be, 1,000 divided by 0.5 is basically 1,000 times 2. So this will work out to be 2,000 Newton meters. And that is what F sub S is going to be equal to. So summing our torques is very powerful, especially since we're kind of guessing, and granted it was an educated guess, that this force down here was going to be equal to 1,000 newtons. I was guessing, but I was treating this like a teeter-totter. But sometimes when you sum the forces in the y direction, it fails, especially if you have an unknown. Okay, so when it comes to rotation, it's very important to sum the torques. So most of us would choose that this reading is going to be 1,000 or 500. It's rare when we think it's going to be heavy. This force up is going to read a heavier force than this force over here. But when you think about it, this force is 1,000 newtons and it's at the 1 meter mark. So that's going to have to, since this force over here is at the halfway mark, well, in order for this to be 1,000 to be equal to 1,000 newton meters up, to balance out this 1,000 newton meters down, you've got to make this 2,000 newtons up times 1/2 meters, which equals to 1,000 newton meters torque right there. So it does kind of make sense practically too. But I wanted to do this problem to actually take you through the process that we're going to actually do on all of our statics problems. And this process is going to carry through for dynamics, which is in 5.3.2. Okay? Well, let's do some more problems. Okay? Here's another problem. And this is kind of more of a conceptual problem, but it's a lot more involved. This time, we're just going to concentrate on summing the torques, okay? But let's suppose you're looking at a shelf on a wall, and the shelf is attached right here by a hinge. And let's say there's maybe a couple strings or something attached all over the place. There's a force pointed up. There's another force pointed up. There's a force pointed up and to the right at 30 degrees. There's another force pointed to the left. Over here at the hinge, there's a force attached to the hinge. And that's F, which is F divided by 2. All 4 of these forces are equal to 4 newtons. So what they're saying in this problem is, if this lever arm is again, it's 1 meter. If all 1, 2, 3, 4, 5 of these forces are equal to F, what does W have to be in order to keep this at a static state, meaning it's not spinning in any direction? So what does this force W have to be in order to make sure that alpha is equal to 0? And I'm also going to say this, it's not spinning either. So it's not spinning or moving in any direction. Okay? So let's go through the process in kind of an advanced problem of just summing the torques and then finding the torques at each one of these points and noting all of our angles and stuff, and then summing the torques. So we're just basically doing this part of the problem, okay? And this is probably, interesting enough, this is probably one of the hardest problems you could do because it's got everything in it, okay? So let's make our notes just like we did before, okay? So here's the pivot point. We're going to choose this as the pivot point, okay? So here we have a force which is at 0 degrees to that pivot point, right? It's at 0 degrees to the lever arm. So that's not at 90 degrees, it's 0 degrees. So that's one thing. Also, it's located at the pivot point, so its R is equal to 0. And this force pointing to the right, this F divided by 2 force pointing to the right, is not going to spin the lever arm clockwise or counterclockwise. It's just going to kind of pull it out. So when you look at all the values that we have here, R is equal to 0, sine of 0 degrees, which is equal to 0. And this force right here, not having a torque at all of that basically says that this force right here located at the pivot point is going to have a 0 torque. Okay. Since it's a complicated part, we're going to choose that as our pivot point. Okay. And plus they marked it, the hinge here. So I think they're implying in this problem that this is the pivot point. But I'm still going to note all of those torques right there. Okay. So you got, it's got a 0 meter. This force F over 2 is 0 meters away from the pivot point. So basically, this is going to result to be in a 0 torque. Okay. Realizing I'm going to need a lot of room for this problem. Okay. So we just started here, and then I'm moving outwards. Okay. Now we get to this point right here. This force up, which is just like the other ones, is going to be spinning this force up, F, is going to be spinning our lever arm. It's going to want to spin it with a positive Z. It's going to be a positive Z torque. It's located at the ½ meter mark, and it's at a 90 degree angle. So that force is going to be positive Z. It's located at the 0.5 meter mark. 0.5 meter mark. And it's a force F, which I think we're saying is 4 newtons. So maybe I should have erased this, and I'll just call this 4 newtons here. Well, it's 4 newtons divided by 2, so I'm just going to actually put in this is 4 newtons right now. And it's at sine of 90 degrees, which again is equal to 1. So this is going to be 0. I'm just kind of keeping a counting of this. This is 0.5 meters times 4 newtons. So this is going to be 2 Newton meters, again, times 1. All right. So coming over to here, now we're at this force here, which is the weight force, which is what we're trying to determine what that has to be if all of these are attached and they're all 4 newtons. This is at 90 degrees. This would be spinning our lever arm clockwise, so that's going to be a negative Z torque. And it's also located at the ½ meter mark. So that force is going to be a negative torque. It's located at the 0.5 meter mark. The name of the force is W, and this is sine of 90 degrees, which is going to be equal to 1. So that is going to be responsible for a negative, again, this is 0.5 meters. So this is going to be a negative 0.5 meters times W times 1. Moving along, we get to this point right here. Now here we have 3 forces. Okay, so let's talk about this force right here. This force is located at 180 degrees. So this is 180 degrees to the pivot point. Okay, it's pointed to the left, which is not going to have a torque, and it's 1 meter away from the lever arm. So all of these forces here are 1 meter away from the lever arm. So I'm going to put that right here. Okay, so that force is going to be, it's neither positive nor negative, so I don't know what that is. It's providing no torque. It's just pushing the whole lever arm in on the hinge. But I'll make it positive. It's 1 meter away. And it's the force of 4 newtons, but it's the sine of 180 degrees, which means that is going to be equal to 0. So that is going to be just 0 Newton meters torque. Got to put the units on this guy. So that is just 0 Newton meters. So we have two forces, this F over 2 force and this F force, both are resulting in 0 torque. Now let's talk about this force. This force is at a 90-degree angle. It's also going to be spinning the lever arm with a positive Z. And it's located 1 meter out. So that's going to be positive 1 meter, 4 newtons, sine of 90 degrees, which is equal to 1. So this is going to be 4 newtons times 1 times 1 meter, which is going to result to 4 Newton meters. Okay. All right. Moving right along, we're down to our last force. This is one of the more complicated ones here. It's interesting if we think about it, but this force here, which is 4 newtons, it's at a 30-degree angle, which means it's pulling it out to the right, but it's also pushing up at the lever arm. Again, both of these arrows here are actually located at the 1 meter mark, right? So, but it's resulting with a force, if this is the force F, up and to the right at 30 degrees, this would be like F cosine of 30 degrees, right? But the only component of this force that contributes to the torque is the one that is at a 90-degree angle to the lever arm, which is going to be F sine of 30 degrees, okay, which is located at the 1 meter mark. So even though I drew it out here, it's actually located at this point right there, which is at the 1 meter mark. So that's the reason why that's, if you didn't get that from the 5.3.0 video, that's the reason why that torque is the sine of 30 degrees. So I'm going to make note of that force right there, that this force is going to also be spinning it counterclockwise. Well, it's spinning it counterclockwise, but it's also pulling it out to the right at the same time. So that's located at the 1 meter mark. It's 4 newtons sine of 30 degrees. Okay. And that sine of 30 degrees is 1/2. So that force right there is going to be equal to, well, that torque is going to be 1 meter times 4 newtons times sine of 30 degrees, which is 1/2, which is going to result in 2 Newton meters. Okay. Now again, when we sum our torques, we set it equal to I alpha. Just like whenever we sum our forces, we set it equal to mass times acceleration. But since it's not spinning in any direction, because it's in a static state, that whole thing is going to be equal to 0, which means this is all going to be equal to 0. Okay? And since we're being really diligent about taking this and doing our accounting right here, this problem is actually going to be pretty simple to solve, which starts out looking pretty scary, but it's actually very simple. So we're going to do some addition and subtraction. We're only going to do addition and subtraction on the black torques, because our red torque has a variable that we're trying to determine. So 0 Newton meters plus 2 Newton meters, that's 2 Newton meters. 2 Newton meters plus 0, that's 2 Newton meters. Plus 4 Newton meters, now we have 6 Newton meters. Plus 2 Newton meters, which is going to be 8 Newton meters. So when we sum all those black torques, that's going to be 2 plus 4 plus 2, which is going to be 8, positive 8 Newton meters. Here we have our negative 0.5 meters times the weight, which we're trying to determine that force right there. And let me just do this. I'm going to grab this and move it a little bit closer so it looks a little bit cleaner. And there we go. Now to solve for the weight of this, I'm going to add this to the other side. So 8 Newton meters stays on the left-hand side of the equation, but the 0.5 meters is now on the other side times the weight force. So now we're going to divide both sides by 0.5 meters. So 8 Newton meters divided by 0.5 meters is what we're determining. And that's going to be equal to our weight force. So this is going to be equal to 8 divided by 0.5. That's going to be 16 newtons. Oh, you know what I just realized up here? That should be just a 2,000 newtons. I don't know why I put 2,000 Newton meters. It's just we're trying to determine the force. So this weight force here is just going to be 16 newtons. That's what it's going to has to be in order to balance out all of these forces, all of these F forces. Okay. So that's probably one of the hardest problems you could do. And that just illustrates how you sum your torques just very carefully, right? So moving right along, let's do some problems that you would run into in the homework, okay? So here's a really good problem. It says right here you've got the bones of a forearm, and it lists off all the little components of the forearm. What it's saying here is that the forearm bones, the bicep muscle, connects at 2.5 centimeters away from the elbow. Okay. And here we have, so let me back up the problem a little bit. It says the mass of the forearm right here, the entire mass of the forearm is 2.35 kilograms. Okay. And the length of the forearm from the elbow to the mass right here is 0.445 meters. Right here it is saying that a person is holding a weight in the hand of 5.75 kilograms. And it wants to know how much force is exerted up by the bicep muscles to hold this weight in a static state. Okay? So we're going to use the process that we did right up here. Okay? And we're going to do a much simpler problem, but it has some numbers. And since we already know the answer to this, but we're basically going to kind of confirm this answer, which is 1410. Okay. And I think they kind of rounded up. They didn't, so I think they rounded up in this problem. So we're probably going to get a decimal place that we're going to have to round up to the 10 mark. So here we go. Let's take a look at our arm right here. So what they said is that the bicep muscle in the problem is pulling up, and I'm going to call this the force of the bicep, F sub B. Okay. And they said that we're going to that here is the elbow joint, and that bicep muscle is attached 2 centimeters, 2.15 centimeters away. So that's 0.0215 centimeters from the elbow. They also said that in this problem, that you have the forearm, which has a weight of 2.35 kilograms. The forearm has a weight down, so the weight of the forearm down. And I'm pretty sure that they're implying that the center of mass of the forearm is right perfectly in between the weight and the elbow. And so if the length of the full arm is 0.445 meters, then this is located at half of that length. Okay, so I think that they're implying that this force is attached 0.445 meters divided by 2 away from the pivot point, which is going to be the elbow. Again, we could choose any of these as our pivot points, but let's go ahead and do it this way for now. They're also saying that the hand force has a weight down, and this is the weight of the what do we want to call this? This is like we'll just call that the weight down, and that this weight is located 0.445 meters away from the elbow joint, which is a pivot point. So right now, initially, we're going to choose this as our pivot point. Okay? We're going to do this problem a little bit quicker than we did the last problem. Okay? The bicep force is going to be spinning, so starting from the elbow joint here to the pivot point, this bicep force is going to be spinning this counterclockwise, which is going to be positive Z, and it's 0.0215 centimeters away. This weight force is going to be spinning it clockwise, which is going to be negative Z. And this other weight force is also going to be spinning this clockwise, which is negative Z. All right. So once you have all your variables determined, right here, we're going to copy them over here. All right. So starting here with the bicep force, it's going to be a positive Z, is 0.0215 meters away from the pivot point, times F sub B, and that's at 90 degrees angle. I'm not going to, well, I guess I'll write sine of 90 degrees. So again, that's just equal to 1. So that force, or that torque, is 0.0215 meters times the bicep force. Moving right along, here we go. We've got this torque right there, which is going to be a negative Z torque, and it's 0.445 meters divided by 2 times the work, times the weight of the forearm, times sine of 90 degrees, which is just 1. So this is negative 0.445 meters divided by 2. You know what? I'm going to take my calculator, and I'm going to actually figure that out right now. 0.445 divided by 2 equals 0.2225. So I'm actually going to rewrite this to be 0.2225. So this right here is 0.2225 meters times the forearm weight. All right. Moving right along, we get to the weight, the weight that the person is holding in their hand. Okay, so that's a red torque. That's going to be a negative torque. That's located at 0.445 meters. And that's the weight. So that is just going to be, again, I forgot the sine of 90 degrees, which is just 1. So this is just going to be 0.445 meters times the weight. All right. Again, we're going to set this top one all equal to I times alpha. Again, since it's not spinning or moving in any direction, it's in a static state, I times alpha is going to be equal to 0. So this is going to be equal to 0. Now what we're going to do is we're going to insert our values for the weight of the forearm, which is 2.35 kilograms. So we're going to kind of whittle this problem down to where we just get numbers over here. So this is going to be 0.0215 meters times the bicep force. This purple force right here is going to be 2.35 kilograms. So this is 0.2225 meters times 2.35 kilograms times 9.8 meters per second squared. So this is the purple torque now with our numbers. So that's the full weight of that forearm times its location from the center. And then our red torque is going to be 0.445 meters times 5.75 kilograms times 9.8 meters per second squared. That's going to be equal to that's it. That's going to be equal to 0. Okay. All right. Let's figure out what these are number-wise. So let's just do that multiplication really quickly. So this is 0.0215 meters times the bicep force. That purple force, which is going to be negative, we're going to have to put some stuff in our calculator. So that's going to be 0.2225 times 2.35 kilograms times 9.8. So that's going to be 5.124. 5.124 Newton meters. Newton meters. Okay, so I multiplied all that out, 0.2225. All right, let's do the red torque now, which is going to be negative. So that is 0.445 times 5.75 times 9.8 equals. So that red torque, a little bit more complex, 25.076. 25.076. 25.076 Newton meters. And again, that's equal to 0. So now let's put these two numbers together. So we're going to add to that we're going to add to that 5.124. So which is 30.199. So I'll call that 30.20. So the red and purple, when you put it together, 30.20. So this is 30.20 Newton meters when you put these two numbers together. 0.0215 meters times the bicep force. Okay. I'm going to add this to the other side. So that negative 30.20 is going to become positive 30.20 Newton meters. And this is 0.0215 meters times F sub B. And so now we're going to have to divide this onto the other side. So that bicep force is going to be equal to 30.20 Newton meters of torque divided by 0.0215 meters. So I'm going to take that force, I'm going to divide it by 0.0215, and we get 1404. So we did some rounding, but our answer is 1404. And I think somehow we rounded ourselves out of the 10 mark right there. So actually, if we round this up to 6.3 newtons, which is 1405 newtons, which, yeah, I guess you could round that up to 1410 newtons. So our answer is correct if we consider rounding to the 10 mark here. Wow. So this is an interesting problem. As you can see, it's really not that bad, not in comparison to what we have just done over here. Okay. But this says something really interesting about the nature of the bicep force. So to put 1410 into terms of how much that is, okay, let's actually figure out 15.75 kilograms. We multiply that by 2.2. We get it into pounds, which is roughly the weight. That red weight is roughly, what was that? 13 pounds. So roughly 13 pounds. This weight down, if you're holding a weight of about 13 pounds of force, okay, 5.75 kilograms times 9.8, which would be basically 57.5 newtons. Actually, anyways, so that would be roughly 13 pounds. Well, this bicep force, if we divide that by 9.8, so to put that in terms of pounds, we take that bicep force, which is 1410 divided by 9.8 equals, that's how many kilograms of force that is. Multiply that by 2.2. This is how many pounds of force that bicep has to be pulling up in order to hold a 13-pound weight. So that's 317 pounds of force. So what is that saying? Well, that means with this bicep, in order to, since the bicep is attached only 2 centimeters away from the elbow, it has to pull up with 317 pounds of force in order to just support a weight that is 13 pounds. That is incredible. That is a huge amount of force that the bicep has to pull up just to support only 13 pounds. That's not that much weight. It's amazing how these problems work out. and putting things in context, it's amazing how our bodies are actually just built and designed for balancing out forces. That's amazing. To hold up 13 pounds, your bicep is pulling up about 317 pounds of force. Moving right along, this is one of your homework problems. And in fact, we're not worried about the direction of the forces in here, but this is going to be one of your homework problems that we'll do in class. Okay, but suffice to say, it's very similar to this problem, but instead of a weight force down, this weight force is going to be up at an angle. Okay, and just to give you a real quick run through, they want to find the tension in these two cables right here. So there's two of these cables, and they want to find the tension in each of the cables, right? So just doing a real quick run through, they're saying basically in this problem, here's the pivot point right here. You have the weight of this entire lever arm is down right over here. And it's located 1.5 meters away from the pivot point. And that's going to result in a negative torque right here. They say also there's a car at a car's weight down. So you got the weight of a car down. Well, this is the weight of the entire lever arm. I should say this is weight sub L. This is weight of the car. And that car is located at the halfway point from here to here. So it looks like this full lever arm right here, this is 9 meters out. So the weight of, and I should use purple for that. So this is 9 meters out. That's where this is. So this full lever arm is 9 meters. So that means this weight of this car is located at the 4.5 meter mark. And that's also going to be a negative Z torque. And they're saying these two tension forces are located at the very end. So this is 2T, which is going to be pulling it up, but also in. So this is going to result with a negative, well, the up portion is going to result with a positive torque. So that's going to be a positive Z. And I got to be careful, that's a 2T, not it right there. And that's 40 degrees. So when you go to some of the torques on this, you'll get something pretty simple. In this problem, starting from the pivot point to the weight of that thing, you'll get a negative 1.5 meters. The weight of the entire lever arm of the bridge, and that's sine of 90 degrees, which is just equal to 1. Okay. Then we go on to the weight of the car. So we start at the pivot point, moving further out. The weight of the car is also going to be a negative Z torque. It's located at the 4.5 meter mark, and that's the weight of the car. And then we get to the very edge now. That's going to be a positive torque. The cables are located at the 9 meter mark, and there are two of the cables. You know what? I forgot to write for the car. That is going to be at the sine of 90 degrees, which is just going to be equal to 1. So moving back to the two tension cables, that's going to be a positive Z, 9 meters. There's two tension cables, so 2T times the sine of 40 degrees. Okay. So over here, again, I times alpha is going to be equal to 0. So multiplying this out, all this is just going to be negative 1.5 times whatever weight that they give you. For me, the bridge is 2,500 kilograms. For you, it's probably going to be a different value, but you'll just put your value in here. Minus 4.5 is the location of where the car is at. And the car is 900 kilograms. That's just the weight of the car times sine of 90 degrees, which is just equal to 1. And then you've got the 2 cables, which is 2 times 9 times the sine of 40 degrees. So 40 degrees, and take the sine of that, which is 0.642787. We're going to multiply that by 2 times 9 equals, so 11.57. So this is going to be 11.57 meters times the tension. Okay, so 9 times 2 times sine of 40 is 11.57, and the meters comes from the 9, and that's going to be equal to 0. So you'll then just put in your values for this stuff over here, and bring it onto the other side. So 11.57 meters times T, that's going to be equal to, I'm going to add this to both sides, 1.5 times whatever weight of your bridge, plus 4.5 times whatever weight of your car. So dividing this 11.57 from both sides, you get 1.5 times the weight of the bridge plus 4.5 times the weight of the car divided by 1.57 meters. So you'll put in your values here, and that should give you what the tension in each of the 2 cables are. Okay, so it's just a real quick walkthrough of that homework problem. Again, there might be some different values that you're given, but yeah, that's a really fun problem to do. Finally, for the last part of this section, we've got a ladder problem right here. Okay, and we'll talk about this as a ladder problem, but basically in this problem, this is in your textbook, you've got a ladder that is 3 meters long, and it's up against a wall, which makes 60 degrees. They're saying that the center of mass of this is going to be where the pivot point is going to be at. So when this, I think what they're saying is this is going to slide down the wall, and this is going to it's going to want to slide down the wall, and this doesn't want to move to the right. So they're choosing this black dot as their pivot point, I believe. I don't know why they put the black dot right there, but we'll find out. But basically, if this is trying to slide down here, you've got a static friction force pushing up right here. So that would be a static friction force, U sub S, times the normal force, right? So the wall leaning against this thing right here, the wall is pushing this ladder out with a normal force to the right, and a static friction force is holding it up, and we'll call this the where these 2 forces are at. Okay, the ladder itself has a weight down, and it's the mass times gravity of the ladder itself. Okay, if this were allowed to slip, right here, it would have a normal force up. So this is, we'll call this N2. But if it were allowed to slip, this would be sliding to the right. So that means you have a static friction force pushing it to the left. This is up, which is positive, to the left is negative. Okay, So, and what they're asking is what is the value, and I think they're assuming that this mu sub s, this purple mu sub s, and this black mu sub s are both the same. Okay. Okay. But they're basically saying that what is the coefficient of static friction with the ground that prevents the ladder from slipping? Okay. So in this problem, what they're doing, so here's their little force diagram. They don't really care about the static friction force that was holding this up, even though I'm convinced there should be a static friction force up. They're basically saying this is the only static friction force keeping it in place. So what they do is they do a mini force diagram. So to be consistent with that, even though I disagree with them, let's not worry about this. They're just saying that this static friction is the only one here. So the first thing that we're going to do is we're going to sum our forces in the x and y direction. So I'm going to do the coordinate system again. Okay, positive x. That looks like a y. Let's make sure that looks like an x. Negative x, positive y, and negative y. So we want to determine mu sub s, given all this other stuff. So I'm going to write all these forces on top. I'm going to have the purple force pointed to the right, and that's just the normal force of the wall pushing it out. And I want to make sure my new numbers are consistent with theirs. So they're calling that N2. Okay, so we'll call this, we'll call this N2, and we're going to call this black guy N1, this little black normal force N1. So that purple force is N2, and that's the normal force of the wall pushing the ladder out. Okay, we have an mg force down, so that's going to be negative mg. We have a force N2 that is pushing it up. It's actually holding up the ladder itself. And we have the static friction force pushing it to the left, which is negative mu sub s times the normal force. Okay. So we're going to sum our forces, and then we're going to look at our torques. Okay. And I might do this slightly different from the way the textbook does it. Sum the forces in the x direction. So you got mu sub s times normal force 1 plus normal force 2 to the right. And that's going to be equal to mass times acceleration in the x direction, which is 0 since this is not moving or accelerating. So basically, this is the sum of forces in the x direction. Sum the forces in the y direction. So we have N2 pointed up. Well, actually, that should be N1 pointed up. Sorry, this normal force is that friction force. So that should be N1 pointed up. N2 is over here, it's purple. Normal force pointed, N1 pointed up. We have the weight of the ladder itself pointed down. And that is going to be equal to mass times acceleration in the y direction, but since this is not moving or accelerating in any direction, that's equal to 0. So N1 minus mg, that's going to be equal to 0. Okay. So let's now take a look at the torques. Okay. There might be some trigonometry, and the way I do it is a little bit different from the way they do it down here, but we'll talk about the differences. Okay. But what we want to do is take a look at the torques. And so we want to choose a pivot point, which is going to eliminate some of our problems right here. Okay. So, here's what I'm thinking. We need to determine, why is that moving all over the place? So we need to determine a pivot point. So it could be rotating around the center of mass, which would be a good pivot point, but that would eliminate mg as a force, right? If we determine the pivot point to be here, that would remove these two forces, both the friction force and the normal force 1. Okay? And that's not good because we need to find out what the friction force is. N2 up here, we know N2 has to balance out with the friction force, but N2 is not really giving us any information. So what I'm suggesting is that we make it spin, because we could choose any as our pivot point. Let's choose this as our pivot point, okay? And so that means these forces here are going to be a full distance 3.0 meters away, okay? And that this force right here is going to be a distance 3.0 divided by 2 away, right? But there's going to be some trigonometry problems here, right? So we're going to have to, by choosing this as our pivot point, which is our only choice to actually determining the friction, that's going to make some of these other forces, determining these forces, there's going to be a lot of trigonometry here. Okay? So, how do we do this? Well, let's start. So I'm going to do this with brute force. So here we go. We have the mg force, right? So this is the lever arm. So the component of the force that contributes to the torque has to be perpendicular to the lever arm, right? So I need to make I'm going to make some little triangles here to show you why I'm struggling with something here. So that mg force is pointed down, straight down, right? But the lever arm, which I'm going to use as green as my lever arm, is right along this point right here, okay? So if I zoom in on that, this torque, this mg force down, which is right here, that is actually a hypotenuse. That torque is pulling the lever arm down. It's pulling the lever arm this way, but also down to the left, okay? And since this makes a triangle, this angle is 30 degrees, right? So this is 30 degrees. That means the only component of this torque right here, of this force that contributes to the torque, is going to be mg sine of 30 degrees, right? Just this component is the angle. Got it so far? So when we go to some of the torques, this is going to be spinning the ladder. The mg force is going to be spinning the ladder clockwise. So that's going to be a negative z torque. It's located at the 1.5 meter mark. And its force is mg sine of 30 degrees. Okay, so let's start summing the torques now. So the first torque that we're doing, summing the torques now, the first torque that we're doing, starting from the pivot point, is this red mg torque. And so that's a negative z torque. It's 1.5 meters away, and that's going to be mg cosine of 30 degrees. Okay? Now we go to the normal, this normal force right here. So I'm going to try to draw some stuff right here. I'm going to draw this green arrow down. Okay. And again, I'm going to say this right here. Actually, let me erase that. I got a little too crazy here. And they said that this is 60 degrees. So I'm just drawing this part right here. Okay. All right. So that N1 force is attached right here. It's pulling it straight up. Okay. Which means this angle is 30 degrees. And that's a hypotenuse because it's pulling this lever arm out. So this N1 force is pushing it out away, but also up towards the lever arm. So this the only component of this torque, of this N1 torque, is the perpendicular component, which is the sine of that 30 degrees. Okay. So by that triangle right here, this triangle that I drew, this black triangle, is right along in here. That N1 torque is going to be, so that's going to be a positive torque. So again, this is going to be spinning it counterclockwise, so that's a positive Z torque. It's 1 meter out. So it's a positive Z torque. It's 1 meter out. And that's going to be N1 sine of 30 degrees. So that's that one. Okay. Now let's take a look at the torque caused by this static friction force. Okay. So again, I'm going to draw the ladder. And I'm going to take this force right here. And I'm actually going to put it this way. Right here. So this is the static friction force times N1. It's pointing to the left. Again, it makes a 60-degree angle here. And again, that is a hypotenuse. That force, boy, that as a line and an arrow, that's very bumpy. So that static friction force is pointed to the left, which means it's pulling it down and pushing it up along the lever arm. And so the only component of that static friction force is the one that's perpendicular to the lever arm. So that's going to be mu sub s times the normal force. Okay, and that's going to be a negative Z torque, and it's going to be sine of, I need some room. So this component right here is going to be mu sub s times normal force 1 sine of 60 degrees. And that's going to be the only component that's perpendicular to the lever arm. And that's going to spin it clockwise, right? So that's pointing down. So it would be spinning it, clockwise. So that's a negative Z torque, and it's 1 meter out. Okay. So once we kind of realize that those torques, and sometimes I have to write little triangles off to the side to track the torque. That's a negative Z torque. It's 1 meter out. And that force is mu sub s, normal force 1, sine of 60 degrees. Okay. Again, always sum your torques like you sum your forces, set it equal to I alpha, but since it's not slipping, that's going to be equal to 0. Okay? Okay, before we get into this, we need to do something with here. And we know mu sub s times N1 is equal to N2, right? But from here, from this force diagram, you could see that N1 is going to be equal to mg, right? So all these N1s are going to be equal to mg. So I'm going to replace all of those N1s with mg. That's cosine of third. Did I say cosine in that? That should have been sine. I don't know why I had cosine there. That should be sine of 30 degrees. And that should be sine of 30 degrees. I wrote sine of 30 degrees there, but over here I wrote cosine. I'm not sure why. All right, so continuing on, sorry about that small mistake. N1 is going to be equal to mg, so I'm just replacing that N1 with mg. Sine of 30 degrees. Negative 1m mu sub s mg sine of 60 degrees equals 0. Since all of these have an mg in it, you could divide both sides by mg, which basically is just going to get you, it's just going to leave you this. You're going to eliminate that. That's just going to become 1. So negative 1.5 Newton meters. Sine of 30 degrees is a half times 0.5 meters plus 1 meter time 1 Newton meter. So mg is, so this is going to be 1m times mg, which got eliminated. So this is going to be 1 Newton meter times 0.5. 0.5. No, I suppose I could have eliminated that sine of 30 degrees too. So I suppose I could have eliminated some more things, but we're just going to continue on with this. And sorry, I was having some screen problems there. So this is, again, this is just going to be 1 Newton meter. This part is 1 Newton meter times 0.5. Sine of 30 degrees is 0.5. Now we're getting into here. Again, we've eliminated the mg, so this is going to be negative 1 meter times the sine of 60 degrees. So I'd take 60 degrees and take the sine of that. Take the sine of that, which is 0.866. So this is going to be minus 0.866 Newton meters times mu sub s equals 0. So here we are. We've got the red and the black force, which we can now reduce down to make even easier. So we're going to add those two together. Well, actually, rather, we're going to subtract them. So we've got so 1.5, which is a negative number. So negative 1.5 times 0.5 equals, and we're going to add to that 0.5 equals. So negative 0.25. So putting these two together, we get negative 0.25 Newton meters minus 0.866 Newton meters mu sub s equals 0. These two are negatives, so you could just make those positives. But either way, we've got to add that. So we could actually just make these two positives, 0.25 Newton meters, plus 0.866 Newton meters mu sub s equals 0. And then finally, we're going to add this to both sides. We could, well, I suppose we could, anyways, we're going to put it onto the other side. So here we go, 0.866 Newton meters mu sub s. Bring it on the other side to get negative 0.25 Newton meters. And then we're going to divide both sides by that. So negative 0.25 Newton meters divided by 0.866 Newton meters. Okay, so let's put that in the calculator. 0.25 divided by 0.866 equals 0.29. So the negative is just kind of unimportant. You can't have a negative value for mu sub s, so that's just kind of a math thing. It kind of worked out. So this works out to be 0.29. So what this is basically saying is that the minimum value of mu sub s that we find that this has to be to hold up this ladder is 0.29. Okay. Now the way I did it is a little bit different from your textbook, but this is I would say this is a very difficult problem. But your textbook does it a little bit differently. Okay. They're using cosines and sines in here. So check out this problem in your textbook and see how they did it. Because they're basically choosing to have it rotate around, which looks like they're using their pivot point as this. So they're actually rotating it around the entire, they're rotating it. They chose this black dot as their pivot point, where I chose my black dot as a pivot point up there. They're choosing theirs as down here, and they're getting the exact same answer that I did. So it just kind of goes to show you that you could choose whatever you want as your pivot point. Either way, you're going to get the minimum value. Okay. And that concludes 5.3.1. Thank you.